Next, what we're going to do is learn how we can use calculus to sketch graphs of some functions. And we're actually going to need quite a bit of build-up before we can actually sketch graphs. So first, we have these three corollaries of the mean value theorem. Now in math, a corollary is a small consequence of a larger theorem. So the mean value theorem is a pretty large theorem. And here we have three kind of immediate consequences of the mean value theorem. And immediate consequences we call corollaries. So first, remember, the mean value theorem tells you about derivatives on intervals, and it tells you how the derivative behaves on intervals. So first, let f be differentiable over I. Capital I is just some open interval. In these first two, I didn't want to write a to b, so I just wrote I. An open interval a to b. Let f be differentiable over I. If f prime is 0 on I, then f is constant on I. So here, this says if the slopes of the tangent lines are always 0 on I, then you can conclude from that that the function is constant on I. Second, if f and g, two different functions, are differentiable over I, diff, D-I-F-F for differentiable, and the derivatives are the same on I. So if the derivatives of two different functions are the same on I, then f equals g plus some constant c. So the derivatives, the slopes of the tangent lines are all the same. From the mean value theorem, we can conclude that the functions will then differ by a constant. These first two corollaries, we will use for some results that we cover in Chapter 5, which will be next week. This one, result 3, is one that we will use immediately. Suppose f is continuous on the closed interval, differentiable on the open interval. Part A, if f prime is positive, so if the derivative is positive, if slopes of tangent lines are positive, then f is increasing. Increasing. Maybe I'll underline increasing. So increasing function, an increasing function just like it goes up as x gets larger. So I didn't formally define increasing, but an increasing function goes up as x goes up. And similarly, if f prime is negative, strictly negative, and strictly positive up here, so no equals. If f prime, the derivative is negative, then f is decreasing, and a decreasing function would look like that. It'd be going down. So let's look at an example illustrating this third result. So right here, consider the graph of f prime of x. So right here, this is a graph of f prime, the graph of the derivative. This is not a graph of f. It's a graph of f prime. And we want to find the intervals on which f is increasing and then find the intervals on which f is decreasing. And what we're going to do is use this third corollary of the mean value theorem, which says if the derivative is positive, then f is increasing. If the derivative is negative, then f is decreasing. So how do I want to say this? Let's say, notice, let's first do where f prime is positive. So notice f prime is positive on what? Where is f prime positive? Well, f prime is positive where this graph is above the x-axis. So f prime is above the x-axis between -1 and 4. So f prime is positive on that interval. So f is increasing on -1 to 4. If I asked you an example like this, you could just say f is increasing on -1 to 4. You don't have to make that observation. I'm making that observation here to illustrate how it follows from this theorem. That's the only spot it's positive because this is going down and that's also going down. And we'll also notice that f prime is negative. Where is f prime negative? Well, f prime is negative where it's below the x-axis. So over here, from negative infinity to negative 1, and also over here, from 4 to infinity. So f is decreasing on those two intervals. So I'll write that over here. So f is decreasing on negative infinity to negative 1 and 4 to infinity. Notice here we're not including any of these endpoints because this result doesn't say what happens when f prime is 0. F prime is 0 at negative 1 and negative 4. That result doesn't tell us anything about what happens at the points where f prime is 0. One thing we'd like to do is be able to use calculus to differentiate between these two situations. So notice, well, we talked about this a little in the extreme value theorem topic. But right here, that point at the top is a local maximum, and this point at the bottom is a local minimum. And we know that that happens when f prime is 0 or when f prime is undefined. But we don't know if at a given point f prime is 0 or undefined. We can't necessarily differentiate between whether we have a maximum or a minimum. But with that third corollary of the mean value theorem, we can use calculus to differentiate between these. Remember, that third corollary tells us about a function increasing and a function decreasing using the derivative. It tells us if we find where the derivative is positive, that we know the function is increasing there, and if the derivative is negative, the function is decreasing there. Well, look at this first example. Until we get to this local maximum, the function is increasing. And then after it, the function is decreasing. Similarly down here, the function is decreasing until it hits that point, and then it's increasing. Well, we can use calculus to differentiate between them now, and we call that result the first derivative test. So for the first derivative test, let x be a critical point for f. So a point at which the derivative is 0 or undefined. Undefined would be if this is like a point, like an absolute value type graph, or a cusp, instead of a rounded off mound. So let x be a critical point for f. 1. If f prime is positive to the left of f and f prime is negative to the right of x, then f has a local maximum at x. And we can see that in this first example here. If f prime is positive to the left, well, I said increasing over here. With that third corollary of the mean value theorem, increasing would tell you, well, the derivative being positive would tell you that it's increasing. So right here, f prime is positive to the left, it's increasing, and f prime is negative to the right, it's decreasing. That tells you that the function has a local maximum at x. And similarly, number 2, if f prime is negative to the left, meaning if it's decreasing, and f prime is positive to the right of x, it's increasing afterwards, then f has a local minimum at x. And part 3, if f prime has the same sign on each side of x, so if it's positive on the left and positive on the right, or negative on the left and negative on the right, then f has neither a local maximum or a local minimum at x. I don't have a graph for that on the board right now, but I'll put one right here. So illustrating part 3, this first graph illustrates part 1, this second graph illustrates part 2. So illustrating part 3 will be a graph like this. How do I want to draw it? How about like this? Actually, let's just do the cube root function. Right there, if you take the point x equals 0, well, the function is increasing over here, so its derivative is positive, and the function is increasing over here, the derivative is positive. So on the left of 0, the derivative is positive. On the right of 0, the derivative is positive. And at 0, there is not a local maximum or a local minimum. So let's do another example. Let's do a numerical example. Find the intervals on which f of x is increasing and decreasing, and then classify the local extrema. So let's give a function and then use it. This theorem, it has a lot of words, but you'll notice as you use it, you don't really think too much about the words. You think more about the words increasing and decreasing, because increasing and decreasing are, I don't know, they're easier words to think of, I think. So example, find intervals on which f of x equals what? X cubed minus 3x squared minus 9x minus 1 is increasing. Find intervals on which is increasing or decreasing. Well, I guess then it's not going to be and. Find the intervals on which it's increasing and find the intervals on which it's decreasing. Find intervals on which f is increasing, decreasing, and classify the local extrema. I'll say extreme. I was going to write extreme values. I'll just say extrema. And I said extrema, but I was going to write extreme values. So with this first derivative test, what we have to do first is find the derivative and find where the derivative is positive and find where the derivative is negative. And to do that, it will be helpful to find where the derivative is 0. So let's do that. I'm going to do it over here. F prime is what? 3x squared, negative 6x, negative 9, positive 0. And we want to set this equal to 0, but let's all those things have a 3 on them, so let's take the 3 out. We're going to want to set this equal to 0. Let's factor it first. So to factor that, what do we have? 3, or negative 3 and 1 make negative 3. Negative 3 and 1 make negative 2. So that'll equal 0 when x is negative 1 or when x equals 3. Now the first derivative test does not tell us that what happens at 0, or what happens when the derivative is 0. It doesn't tell us that those are relevant. They are relevant in that we can use them to figure out the intervals on which the derivative is positive or negative. Now, maybe I'll write a half sentence. So, to find intervals on which f prime is positive or negative, we will do the following. We're going to use a number line. There are a couple other ways you can do it. I like using the number line. And especially when we do graphs, I like the number line. And what we're going to do is mark off the points where the derivative is 0. If this weren't a polynomial, I'd also say we need where it's undefined, but we don't need where it's undefined here because it's defined everywhere. But we do need to mark off where the derivative is 0. And now, in each of these pieces of the number line, each of these 3 pieces, the derivative will have the same sign. So over here on, what, negative infinity to negative 1, all we need to do is find f prime at a certain value in that interval. Let's choose negative 2. F prime at negative 2. Now f prime at negative 2, you could go through and find the actual number. What would it be? It would be 12, 3, I lost myself. 15. You could do that, But remember, the first derivative test and that corollary of the mean value theorem tell us that the sign of the derivative is what matters. So the actual number does not matter. The sign is what matters. And to do the sign, well, to find the sign, well, remember, negative times negative is positive. Negative times positive is negative. Well, we have f prime written as the product of three things here. So all we have to do is keep track of the signs of each of these three pieces at negative 2. So at negative 2, 3 is positive. Negative 2 minus 3 is negative. Negative 2 plus 1 is negative. So we have positive times negative times negative. Two negatives make a positive. How about this middle interval between negative 1 and 3? Did I write that like that? I'm debating if I want to put these under rather than over. Now I'll leave them over. A point between negative 1 and 3, I like 0 because 0 is easy to substitute in here. F prime at 0, we have positive times positive, which is negative. And over here, after 3, choose a number larger than 3. I'll choose 4. At 4, we have positive times positive, which gives us a positive. And we can conclude from this, so f prime, or what do we want to conclude where it's increasing or decreasing? So f is increasing on wherever it's positive. So it's positive over here and it's positive over here. So negative infinity to negative 1 and 3 to infinity. So wherever the first derivative is positive, f is increasing. And f is decreasing on wherever it's negative, and in this case, negative 1 to 3. Well, that's half of the answer. So find the intervals on which f is increasing, find the intervals on which it's decreasing. Well, we found them. But now we need to classify the local extrema. And you could directly use the terminology of the first derivative test to classify the local extrema. I don't think I've ever actually thought of it like that. I always think of it in terms of increasing or decreasing with positive and negative. And then I think of the actual graph. Well, I don't think of the actual graph. I think of what a piece of the graph may look like. And with practice, that does become easier. So let's classify the local extrema, first with negative 1. F prime is positive before negative 1. F prime is negative after negative 1. So the function is increasing, and then it starts to decrease. So it's increasing before negative 1, and then it starts to decrease. So f has a local maximum at x equals negative 1 because the function is increasing until it gets to negative 1, then it's decreasing. And similarly, over here at 3, the function is decreasing until it gets to 3, and then it starts to increase because the derivative is negative before before 3 and positive afterwards. So the function is decreasing until it gets to 3, and then it's increasing. So, and f has a local minimum at x equals 3. And you could have also phrased the reasoning using positive and negative as the first derivative test states. And if I had more board space, this last sentence I would have put right after here. So f is increasing here, decreasing here, increasing here. So our goal, we need one more result before we can get to our main goal of this topic, which is sketching graphs. In that, when we do a number line argument like this, I like to also write increasing and decreasing right on the number line, because actually writing out this sentence when we're doing the graphs will just get in the way. So you could also, when we get to graphs, once you get the signs of the derivatives, you could just write increasing, decreasing, where the derivatives are positive and negative, like that. Just checking that my answers are correct. Yes. So what have we done here? We have applied the mean value theorem to the first derivative. Well, we can also apply the mean value theorem to the second derivative. So let's recall a couple things about how we interpret the derivative. So first, the derivative measures a rate of change. And the notation dy dx, one of the reasons it's useful is because it allows us to think of a derivative as representing how a value or how a quantity y is changing as x is changing. And we understand this as the slope of a tangent line, but using the mean value theorem, we understand this as the slope of the tangent line as it travels through a graph. But the second derivative is just the derivative of the derivative. So the second derivative tells you how the derivative is changing as x is changing. The derivative tells you how the derivative is changing using slope language. The second derivative will tell us how the slope is changing as time is changing, well, as x is changing. So let's look at a couple examples with tangent lines. And we're going to try to figure out how the slope is changing as x becomes more positive. So in this first example, let's look at slopes of tangent lines. Well, the slope of the tangent line right here starts as a positive. What happens as x becomes more positive? Well, the slopes of the tangent line go like that. So it starts like this. The slope of the tangent line starts like this, and then as x changes, it goes like that. Now, what are these slopes numerically? Well, right here we have a positive slope. It's close to 0, but it's still positive because it's going, what, upward. But as x changes, the slope becomes more positive. That's more slanted upward. And as you get up here, it's slanted even more upward. So as tangent lines travel on this curve, the slopes of them become more positive. Well, that's one observation. Let's look at this next curve. Let's start down here. We have this very slanted tangent line. It's a negative slope, and it's pretty far away from 0. I mean, the slope 0 is like this. So this could be like a -5 or a -10, a slope like that. And what happens as this tangent line travels on the curve? It goes like that. So it starts up here, and then it goes like that. So it starts very negative, and as it goes on the curve, it becomes less negative. I hope I wasn't in the way for that. It starts as very negative, and as it travels on the curve, it becomes less negative. So if it becomes less negative, it could be going from something like -10 to, say, -5, then to -1 maybe. But in both cases, so I'll say here, as x changes, meaning as x becomes more positive, the slope of the tangent lines, I should say slopes of the tangent lines, where was it? I step on the microphone. I've probably done that in each video. Here, as x changes, the slopes of the tangent lines become more positive. In each graph drawn here. as x changes, the slopes become more positive. Here it starts at like a positive half, positive 1 maybe, and then all the way over here it gets up to a slope of like positive 5. Here it starts at negative 10, and then as it goes on the curve, it becomes less negative, more positive. What about these two graphs? I'm going to erase that concluding remark. So here we'll have two sets of two graphs, two examples. So that first one you should call example 1 with those two graphs. This next one I'm going to call example 2. And I'm going to draw two different graphs and have a concluding remark. Which one do I want to do first? That one I want to do first. And which one do I want to do second? This one I want to do second. So what about here? How does the slope of the tangent line change as x changes? Well, here it starts as a positive. It's like a positive 2 or a positive 3 or something, but it's positive. As this tangent line travels on the curve, well, that's still positive, but it's a very small positive tangent line. So it starts up here, and then as x gets larger, the slope goes down like that. So it starts as a reasonably large positive number, but then it gets less positive. So it starts at like a positive 3, and then down here it gets to a positive like half maybe. What about in this second curve? Maybe I should use my right hand so I'm less likely to be in the way. When you start up here, we have a negative number. It's pretty close to 0, but it is still negative because it's going downhill. So say like a negative half. But as this travels on the curve, it becomes more negative. So it starts here, and as it travels the tangent line on the curve, it becomes more negative. So up here it starts as a large positive number and becomes less positive of a number. Here it starts as a small negative number and becomes more large of a negative number, where large is in absolute value language. But in each case, the slopes of these tangent lines become more negative. And we're going to use this to define a couple new words and explain the second derivative test. So this first theorem translates what I said in those two examples to a new word to describe graphs like those. Part 1, if f is increasing on a to b, then f is concave up on a to b. And over here, right here I have the two graphs from the first example. Here I have the two graphs from the second example. Remember here, the slopes of the tangent lines were becoming more positive. That's another way of saying that the derivative is increasing. So in these two graphs on example 1, according to this theorem definition, f is concave up on, well, I didn't draw an interval a to b, but let's just say on a to b. Let's say the whole graph is a to b. And similarly, if f prime is decreasing on a to b, then we say f is concave down on a to b. And that's illustrated with these two graphs. Now, to actually visualize concave up or concave down, what I like to do is look at the caved-in portion of a graph like this and see which way it's pointing. So here, the caved-in portion is this side of the graph, and that's pointing in that direction. Over here, the caved-in portion is pointing in that direction, and those are both not pointing downward, they're pointing kind of upward, so we say concave up for those first two graphs. And here the caved-in portion is there, going in that direction, and here the caved-in portion is there, going in that direction, and both of those are pointing down. Now, this is useful, theoretically. It tells us that we would have to find, in order to find where a graph looks like this versus that, it tells us we need to find where the derivative is increasing or decreasing. And we can do that. But it might be more useful to be able to reach these conclusions just by doing a sign argument like we did for the first derivative, and we can do that. The second derivative test. Let f be differentiable on a to b. Part 1, if the second derivative, f prime prime, is positive, then f is concave up. Part 2, if the second derivative, f prime prime, is negative, then f is concave down. And you can see how this parallels the first derivative test. All we're doing here is applying that third corollary of the mean value theorem to the second derivative. Now, as a definition that we'll find useful, so when we were doing the first derivative, when the first derivative changed signs at an x value, we already knew how to describe that as a maximum or a minimum, local maximum, local minimum. Here, if f is continuous and changes concavity at x, so meaning on the one side it's positive, on the other side it's negative, then we say f has an inflection point at x. And let's look at an example of what an inflection point looks like. So f has an inflection point at x since what? Well, I need to give you a graph. So I'm going to finish this thought here and draw the graph down here. How do I want this to look? Let's make it look like this. So x will be somewhere in here. X, we'll call it f. So an inflection point occurs where concavity changes. So right here, on negative infinity to x, we have a piece of a curve that looks like this. So its caved portion is pointing downward. So if f is concave down on this interval, negative infinity to x, and we can abbreviate, concave and up and down are large words, so we'll abbreviate this CC with an arrow for up versus down. So f is concave down on negative infinity to x, but after x, we have a piece of a curve that looks like that, where its caved in portion is pointing upwards. So since f is concave down on that interval and concave up on x to infinity. So at x, f changes concavity. In this case, it changes from concave down to concave up. Now, in this definition, it says if f is continuous and changes concavity. You might wonder what would it look like if it's not continuous. Now, we're not actually going to do any graphs where it's not continuous. We could, but we won't. So example, f does not have an inflection point at x, even though concavity changes at x. And what would that look like? Well, we could have a graph like this. Let's put, I don't know, something like that. What would it look like? Something like this, maybe. So if x is at that asymptote, this function does change concavity at x, because on this side it's concave up, and on this side it's also concave up, but it's not continuous. This one does not have an inflection point there. We would need it to be continuous for it to have an inflection point. Now, with the first and second derivative tests, we actually have everything we need to sketch a graph. But before we do that, I'd like to summarize these results using a few pictures. The sketch of a graph can be found by identifying intervals over which the graph looks like one of these four pieces. And these are those four pieces from examples 1 and 2 from a few minutes ago. The sketch of the graph can be found by identifying intervals over which the graph looks like one of these four pieces, and then piecing together the results. And we're going to be able to use calculus to identify each of these four pieces. So this one here, it's going up. So it's increasing. The caved portion points up. So it's concave up. Well, those are words. In calculus, sometimes words aren't as descriptive as derivative results. Increasing, first derivative is positive. Concave up, second derivative is positive. Well, that's wonderful. What about this next one? Well, this is also increasing. The caved portion points down. So concave down. Well, increasing, first derivative is positive. Concave down, the second derivative is negative. Over here, it's decreasing. The caved portion points upward. So it's decreasing and concave up. So the first derivative is negative, and the second derivative is positive. If you go through all your work and you find that on some interval the first derivative is negative, the second derivative is positive, well, it's going to look like that. And down here, it's decreasing, which has nothing to do with that arrow I just drew. It's decreasing because it's going down, and it's concave down because the caved portion is pointing down. And of course, decreasing, first derivative is negative, and the second derivative is negative if it's concave down. So all we have to do to sketch graphs of the functions we'll see is identify where the first derivative is positive and negative, and where the second derivative is positive and negative, and then putting these pieces together. So let's do 3 examples. We're going to do polynomials. On your final, the graphing question will be a polynomial. I will provide, as a separate document on Canvas, some graphs that are not polynomials. And you can look through some of those, but it's not required. I would recommend looking through some of them, or all of them. So first, sketch a graph of f of x is x cubed, negative 6x squared, positive 9x, positive 30. Well, we need where the first and second derivatives are positive and where they're negative. So let's start with the first derivative. 3x squared, negative 12x, positive 9. Well, let's set it equal to 0 and go from there. Equals what? 3. All of these have a 3 on them. X squared, negative 4x, positive 3. Debating where I want to write this. Let's write it here. I hope I can fit this entire thing on the board. Maybe I'll write it here. Equals 3. Factor that. 3 and 1 make 3. 3 and 1 make 4. So this is 0 when x equals 1 or when x equals 3. Well, great. Let's interpret this on a number line. So here's 1, here's 3, and remember, all we need is the sign of the derivative, because that tells us increasing, decreasing. So here, f prime, let's say at 0, because 0 is in this interval, f prime at 0 is a positive times a negative times a negative. In here, we can choose 2, because 2 is between 1 and 3. F prime at 2 is 0. F prime at 2 is positive times negative. So f prime is negative. And over here, let's choose 4. F prime is positive times positive, which is positive. And I'll just remark down here, increasing, decreasing, and increasing. Well, that's great. Before we do the graph, we will need to do the same thing with the second derivative. Where do I want to do that? Let's do that over here. The second derivative. Sometimes I don't write the of x. I think that gets in the way sometimes. Second derivative, 6x, negative 12, and that equals 0 when x equals 2. You factor out a 6 if you want, or you could just add 12 divided by 6. Well, let's do the same sign chart, because remember, what we're concerned with is where the second derivative is positive and where it's negative. Well, that will occur around where it's 0. So it's 0 at 2, f prime prime. On the left of 2, let's choose 0. Substitute 0 up here, you get a negative. F prime prime on the right of 2, let's choose 3, gives you 18 minus 12, which is positive. Doesn't matter that it's 6, it matters that it's positive. So we have the derivative is negative here, so it's concave down. The original function is concave down. The derivative is positive, so the original function is concave up. All of these derivative tests are designed to tell us information about the original function, because that's what we're going to want to sketch a graph of. So the sign of the first derivative and the sign of the second derivative tell us whether the original function is increasing or decreasing or concave up or concave down. So now, all we have to do is piece together the result. To sketch the graph, I always, before drawing anything, note these points. We have 1 and 3 and 2. Those are going to be the relevant points on the x-axis. Now, how am I going to do this on a narrow board? Well, let's just start and see how it goes. Okay. So let's mark off 1 here. Let's mark off 2 here. Now let's mark off 3 here. And in that marking off, I did look up here for a reason. So we could piece together things like this, and things like that, and things like this, and so on. But that doesn't tell us anything about whether the function is way up here, or whether the function is way down here. So when we're doing a sketch, the first thing I do is mark off the y-intercept. Which in this case is 30. Remember, the y-intercept goes over 0 up something. So over 0 would mean x equals 0. Some cars driving by. That doesn't sound like a normal car. Yeah, it was some sort of motorcycle. 2 sort of motorcycles. Lots of things going around here in northeastern Wayne County at 1 in the morning. Where was I? Oh. So the first thing to do, find the y-intercept. If those noises didn't show up on if the microphone didn't catch those noises, there were some noises going by. Where were we? So mark the y-intercept when x equals 0. And now we just have to piece together those 4 types of pieces. Well, let's start. We marked off the points 1, 2, and 3 because they were the relevant points from our first and second derivative. So the first interval to consider is negative infinity to 1. What happens on negative infinity to 1? Well, the function is increasing and concave down. What does increasing and concave down look like? What does it look like? Increasing and concave down looks like that. So from negative infinity to 1, it's going to have to look like that, and it's going to have to go through that point 0, 30. So maybe I should move that labeling up here. So it'll look something like that. And I'll draw this arrow down here like that. So it's increasing and concave down until we get to 1. That would be the second of the 4 pieces we drew. What about the next relevant interval? 1 to 2. Well, on 1 to 2, it's decreasing and concave down. What does decreasing and concave down look like? Decreasing concave down looks like that. And it looks like that until it gets to 2. How about the next relevant interval, 2 to 3? On 2 to 3, still decreasing, but now it's concave up. What does decreasing concave up look like? Decreasing concave up. No, it's this one. Looks like that. Decreasing and concave up until it gets to 3. So let's draw one of those between 2 and 3. So something like that. Notice here the concavity does change because on this side it's going downward, this side upward. We'll deal with that in a moment. And then the last remaining interval is 3 to infinity. It's increasing and concave up. What would increasing and concave up look like? It would look like that. So let's draw one of those after 3. Now, sometimes I ask, I didn't write it for this one, sometimes I ask, label the local maximum, local minimum, and the inflection points. Sometimes I say to do it with an ordered pair. I'll just say, for this example, with the graph. So with the graph, we don't really have to think of f prime is positive, f prime is negative, and so on in labeling the local maximum and local minimum. So I'll just label these like this. Local maximum, the top of the mound, local minimum, the bottom of the mound. And here we have an inflection point. And if I said to label them with an ordered pair, well, you'd have to label them with an ordered pair. Let's do another example. Now, this is a sketch, so it's allowed to be slightly inaccurate in certain ways, but the calculus definitely needs to be right to get full credit. I mean, so like at the end of that, maybe that function did go below the x-axis, but we're not going to worry about that. Maybe that local minimum went below the x-axis. It might. Next, 2 plus 3x squared plus x cubed. Minus x cubed. Well, we're going to do the same thing. First derivative, positive, negative. Second derivative, positive, negative. So here the first derivative is 6x minus 3x squared. Well, let's factor this. How does this factor? You can pull out a 3. Both of them have a 3. You can pull out an x. Both of them have an x. And you're left with what? 2 and negative x? Yes. And this equals 0 when x equals 0 or when x equals 2. So when x equals 0 or when x equals 2. And we'll use that to build a sign chart. Our relevant points are 0 and 2. We want where the first derivative is positive, where it's negative. So the first derivative on the left of 0, let's choose negative 1. Choose negative 1, you get negative times positive, which is negative. Between 0 and 2, choose a point like 1. You get what? Positive times positive, which is positive. On the other side of 2, choose something like 3. You get positive times negative, which is negative. Well, now let's just label decreasing for where it's negative and increasing for where it's positive. Well, that's great. Now let's do that with the second derivative. Second derivative is 6 negative 6x, which equals 0 when x equals 1. Well, you can factor out a 6. You get, what, 6 times 1 minus x, or you could add 6x divided by 6, or however you want to solve that, so long as it's correct. So let's mark off 1. On the left of 1, say at 0, the second derivative is 6 minus 0, which is positive. On the other side of 1, say at 2, this derivative is 6 minus 12, which is a negative number. So we have concave up over here and concave down over there. Well, now we just have to piece together this graph. So let's do that. What were our points 0, 1, and 2? So So 0 is there, let's say 1 is there, and let's say 2 is there. Maybe I should draw this over a little more. No, that's fine. Let's first mark the y-intercept, which in this case is 2. So 0, 2 is the y-intercept. And now let's, maybe I'll mark 0 like this. Now let's piece together pieces. So the first relevant interval, negative infinity to 0, decreasing and concave up. Decreasing and concave up. What would that look like? Looks like that. Decreasing, concave up until 0. So it'll look something like this until it gets to 0. And again, I wrote that 0, that ordered pair in a wrong, in an annoying spot. So 0, 2. Next relevant interval, 0 to 1. Increasing and concave up. What does increasing, concave up look like? That. Until it gets to 1. 1 to 2 is the next relevant interval. Increasing and concave down. So increasing, concave down would look like that. So let's throw one of these on here from 1 to 2. And then 2 to infinity, decreasing, concave down, decreasing, concave down looks like that. So let's put one of them there. So this function looks like this. And here, let's again label the maximum, minimum. Let's label these with an ordered pair this time. Because these numbers aren't too bad. And the other one, and the numbers weren't too bad, but I didn't feel like thinking about them. So right here at 0, 2, we have a local minimum. What about here at 1, 4? At 1, 4, the concavity changes. Let's try to spell INF right there. Inflection point. Because concavity changes. At 2, what do we get? 2 plus 12 minus 8 is 6. So 2 and 6, we have a local maximum. And here, these are sketches of F. And let's look at one more example, which I don't have memorized, so I have to go look at my notes. Negative 2x squared, positive 5x, negative 2. Well, again, we're going to do the same thing. First and second derivatives, positive, negative. Piece together graph. So here, first derivative. I don't want that of x there. Negative 4x, positive 5. Where does this equal 0? This equals 0 when x equals 4/5. No, when x equals 5/4. Well, let's label 5/4. On the left of 5/4, say it's 0. F prime is 0 plus 5, which is positive. On the right of 5/4, say at 1. 1 is not on the right of 5/4. On the right of 5/4, say at 2, f prime is negative 8 plus 5, which is negative. So we have decreasing, and we have increasing. Well, that's great. Let's do the second derivative. Let's do the second derivative down here now. Let's do it in the same spot I did it over here. F prime prime equals negative 4. Well, where is negative 4 equal to 0? Negative 4 is never 0. So let's say which is never 0. But negative 4 is always negative. But f prime prime is always negative. So we can apply the second derivative test. So f is always concave down. Well, now we just have to sketch this. Our only relevant point is at 5/4. Let's mark off 5/4. Y-intercept, -2. So we have 0, -2. Well, now we just need to piece these together. On negative infinity to 5/4, we have increasing and concave down, increasing and concave down. Looks like that. Maybe I should draw with one line since that's how I did the other 8. Increasing concave down looks like that. Through this point, so let's make that look, I don't know, something like that. And then on 5/4 to infinity, decreasing and concave down, which looks like that. So right there we have a sketch of f, and here we have a local maximum. And you don't have to find an ordered pair for numbers like that. You could. That is not a difficult computation. It's just a fraction with, what, 16 in the denominator? If I say in directions to label the points with an ordered pair, then you have to. If I don't use the word ordered pair, then you don't actually have to find the ordered pair. But there are a few other graphs to try on the worksheet. I think they're probably all a little harder than the ones we've done. Maybe one of them is not a little harder, but definitely at least one of them is a good deal harder than what we've done. So try those, and then try, of course, the one on the homework, and see how they go. But they all follow the same pattern. Find where the first derivative is positive and negative, find where the second derivative is positive and where it's negative.